So not only do the diagonals of a rhombus intersect each other at right angles, but they are angle bisectors, so they divide the angles into two equal pieces. Okay? And since they just are late, just a quick thing and show that. One property of rectangles. Property of a rectangles is that the diagonals of a rectangle are congruent. So notice that, recall that in when we talked about parallelograms, just in general, we said that they weren't necessarily the same, the diagonals weren't necessarily the same length, but they did bisect each other, they cut each other in half. If you have a rectangle, we actually have that the diagonals are both the same length. So they both are congruent if you have a rectangle. Okay, Courtney? So we have three properties: two of rhombi and one for rectangles. Okay, beyond just their definition. So if I ask you to classify or tell me what kind of parallelogram this is going to be, you should be able to give me a name for it, and then knowing that, then let's come up with. So let's find some missing values. Okay. So this first one's a rhombus, and why is this a rhombus? Four congruent sides. This is a quick why, just as a reminder. So the four congruent sides, then, oh boy, so we have two missing values. We have an x and a y. Well, let's see. If we know the sides are all congruent, then this thing and this thing better be congruent. Should be able to figure out what x is here. X is what, 2? Well, x is 2. How are we going to find what y is? Are these things necessarily equal? We said nothing about what the angles of a rhombus are. It still is a parallelogram. What are these kind of angles? Oh yeah, they're consecutive. So we said if it's a parallelogram, then these consecutive angles are always supplementary. So these things should always add up to 180.
I have a question now. Does that mean that S equals 97 and R equals 12y minus 1? Or
Absolutely. Because it's still a parallelogram, so opposite angles are still congruent. So then these two are the same measure, and these two have to be the same measure. So then one thing, how about we say 97 plus 12y minus 1 is equal to 180. So at 96, so let's subtract. Well, 97 minus 1 is 96. So if I subtract 96 from both sides, I get 12y equals what? 84? So y, oh, not 4, 7. Don't ever trust your math. 7, there you go. Y is 7. I was just testing you there. Bad tester, but x is 2, y is 7. Okay. Let's see, what kind of figure is this guy?
A square.
Why is it a square?
Because sides and sides are congruent.
It's both a rhombus and a rectangle, so yes. This guy is a square.
Shut up.
Congruent sides. And congruent angles.
Shut up, Abby.
So then, boy, what's some equations we can set up to find what x and y are?
2 plus 4 equals 5y plus 300.
Okay, we could solve this and you get what, minus 1? We get what? 3 is equal to 3y. Y is 1. 5y minus 4 is 3x. X is 2. And so on. Rectangles, rhombi, and squares. Okay. Those are all special parallelograms. Okay. So anything that's true about a parallelogram is automatically true for these things. Plus we get some more properties based on them being those. So we have all the parallelogram properties plus these extra ones if it's a rhombus or if it's a rectangle or if it's a square, it gets everything. Just kind of cool. The other kind of flip of this is, well, what if we still have four-sided figures but they're not parallelograms? These things are, from here on out, we're going to talk about two main types of quadrilaterals that are not parallelograms. Okay. These are most certainly not parallelograms. We're going to leave that family. The first grouping is called a trapezoid. And a trapezoid is a quadrilateral with exactly one pair of parallel sides. Okay. Parallelograms have two pairs of parallel sides. Trapezoids are, well, what if we pare it down and we don't quite get two, but we get one? One pair of parallel sides gives us what's called a trapezoid. Okay? Trapezoids kind of our common trapezoid could look something like this, where we have, say, like one pair of parallel sides. Again, a very poorly drawn trapezoid, but a trapezoid nonetheless. One pair of parallel sides, but not two. An isosceles trapezoid is a special kind of trapezoid. It's a trapezoid with congruent legs. Okay. Probably should talk about parts of a trapezoid. The two sides that are parallel, the parallel pair, is called the base, or the bases of a trapezoid. So for any trapezoid, the pair of sides that are parallel are called the bases. And then the other two sides are called the legs. So if we get these two sides that are not parallel, if they're the same length, then we have what's called an isosceles trapezoid. Okay. With these definitions, we have a couple properties of trapezoids and isosceles trapezoids in particular. Actually, the first two are going to be more or less an if and only if. It'll be a statement and then its converse. The first statement says that if a trapezoid is isosceles, then each pair of base angles, wow, I just spliced those words together, of base angles are congruent. Base angles being the angle pairs on the bases. So I'm going to rewrite this word over here. So if I have an isosceles trapezoid, then each pair of base angles are congruent. Or the angles formed by the same base are congruent. So that would be a congruent pair, and those two must be congruent. Okay. The converse of this is also true. So if we have a trapezoid where the base angles are congruent, what can we conclude about the trapezoid? If I gave you that this trapezoid has two pairs of base angles that are congruent, then it's going to be an isosceles. Okay, so the converse of this is also true. So if in a trapezoid the base angle pairs are congruent to each other, then it is isosceles. So if you start with those angles, then you know, and they're congruent, then you get the side lengths are the same length. You get their isosceles. So we can know something about the length of the sides. The last property that we'll jot down before we get to some examples on trapezoids is the following. It talks about the diagonals of a trapezoid. So the diagonals of a trapezoid are congruent do we remember what IFF stands for? The diagonals of a trapezoid are congruent if only if it's isosceles. So if you get the diagonals are congruent, then it must be isosceles. If it's isosceles, then the diagonals must be congruent, is what this is our third property. So we have talking about the base angle pairs, and then talking about the diagonals. Yeah. Well, we got a couple examples coming up here that might highlight that. Well, I got a couple angle examples. So let's find the value of the missing interior angles here. Well, this is a trapezoid. It's got one pair of parallel sides. What is this a special kind of trapezoid? Yeah, these two are the same length, so it's isosceles. So what do you know about the angles in an isosceles trapezoid? The base pairs are congruent. So the angle pairs that are created from the same parallel side. So 53 degrees, which other angle is going to be 53? Angle B over here. That's supposed to be. And it's a cutoff B. Let's just write a diagram. Okay, so then what else needs to be true in here? Okay, these two are equal. Okay, if you have parallel lines, what are these two angles called? Not corresponding. Consecutive interior angles between parallel lines. What do you know about consecutive interior angles between parallel lines? Supplementary. Thank you, Andrew. So if they're supplementary, then what does this angle have to be?
127.
Okay, then what's angle C? Yep, there's other ways you can solve that, but those would be your missing angles. Okay. You can do the second one on your own if you'd like. It's pretty much the same thing. Find angle angles B, C, and D. Which other angle should be 97? B? D. So then each of these are what, 83? We have one more property of trapezoids. We're going to do one property, some examples, and we'll look at heights. Then we'll call it a day. I know we're buzzing through a ton of stuff here, but it's life, I guess, today. Trapezoid mid-segment theorem. It says that a mid-segment, oh boy, what was the mid-segment of a triangle? Remember what a mid-segment of a triangle was? How'd you make a mid-segment in a triangle? We did it way back in chapter 5. If you had a triangle, and I asked you to find the mid-segment, what should you do? Or aim, there's 3 of us. No, not
No,
bisects.
you draw a line from like the top to the middle of the bottom.
That's called a median,
Oh.
not a mid-segment.
Mid segment.
Okay, think mid, what's mid gonna mean? Middle of segment. So I'm gonna draw a segment that connects what? The middles of segments. So let's draw a segment that connects the middle. What's the middle of a segment called? What's the point that's in the middle of a segment called? Midpoint. So I'm going to connect midpoints. So if like my midpoint of this segment is somewhere over here, how about I draw a midpoint in here? My mid segment connects this.
Oh yeah.
Okay. And some of you are starting to bring back great memories. Well, how does the length of this correspond to the length of the base? It's half the base. For a trapezoid, it's going to be along that same lines, but it's not going to be just half of one of the bases. The trapezoid midsegment theorem says that the midsegment of a trapezoid is half of the length of the sum of the bases. What's sum mean? Add together. So I'm going to find just not half of one of them. I'm going to add them together and divide by 2. So if I have, say, some trapezoid, we generally call them B1 and B2. The length of the midsegment is add B1 and B2 and divide by 2. Kind of extrapolating, could you apply that same formula to a triangle? Add the 2 bases and divide by 2? Well, if we add this base, what would be the other, what would we want to think of like the other base of the triangle? Like what would we think of like the length of this singular point? It's like no length. So like that theorem is actually, this is actually like a limiting case of that theorem. For a triangle, like its top base just has no length, 0. So like the midsegment is just like this base plus 0, which is just the base. But if you have 2 of them, we're going to add them together and divide by 2. So like some examples of that might be here. So like if I ask you to find, oh, I jumped right into it now. If I ask you to find a missing length in here, so if I want to find the mid-segment length, it's add these together and divide by 2. So I'm going to add together, this is the first base, It's the second base. Then the length of this segment is these things added together divided by 2. So B1 plus B2, half of that is the midsegment. Well, so let's put in expressions for these two and solve. So B1 is 17, or 17 plus 7x minus 5, all divided by 2 is 20. Let's think algebra here. What might be a really great idea to do to make life easier before we do anything else? Get rid of the fraction. What should you do to get rid of that fraction? Yeah, let's multiply both sides by 2. If we do that, we can cancel that denominator. And now we get a nice little couple step equation here. 17 plus 7x minus 5 is equal to 40. And now you can solve this equation. 12x, 7x plus 12 is 40. Seven x is 28. X has got to be 4. Let's set up. See if you can't set this guy up on your own and find x. Some algebra concerns that I saw just a second ago. If I want, applying that theorem, I'm going to add the two bases. So I get 44 plus 10, and I want half of that. So I'll divide it by 2, and that's equal to the length of this midsegment, which is 2x minus 1. So there was some of you, a great way to do this might be just to add these together, get 54. 54 divided by 2 is 27. An equally valid way to solve this might be if I don't want this fraction, maybe we multiply everything by 2. Then I multiply this by 2. Notice that the 2's would cancel, and you get 54 is equal to what? 4x minus 2. Either way, we're going to get the same answer. Because we're going to subtract 2 here, or sorry, add 2, and get 56 equals 4x divided by 4. X is 14. Regardless of how you solved it, you should get 14.
I was like,
if you got 27 and a half, if you got 27 and a half, you didn't divide these two at the sum by 2. Okay. All right, you guys are doing awesome so far. I know this is probably the most we've done in one day yet, but
do we want
okay.
homework? 40-minute homework time.
Yeah, not that much. Our last type of quadrilateral is neither a trapezoid nor a parallelogram. So there are going to be no parallel sides here. However, there is something important. The last quadrilateral is called a kite. It has no parallel sides, but it does have, it's a quadrilateral with 2 pairs of congruent sides. So we are going to have 2 pairs of sides that are congruent, but they're not opposite of each other. It's called a kite because it looks like a classical kite. So if we have, so an example might be, here's a pair of congruent sides, and there's a pair of congruent sides, but are not opposite. So this side is not the same length as this one. This one is not the same length as this one. Okay? We have 2 pairs of congruent sides, but they're not opposite of each other. They're actually very much adjacent. 2 properties of kites. we get one property is that, like a rhombus, the diagonals are perpendicular. Of a kite are perpendicular. Two properties: one, they're perpendicular, and two, the diagonals bisect one pair of angles. And can we guess which pair it's going to bisect? Ben?
They're the ones. The top and the bottom.
Like in this drawing, the top and the bottom. The angle pair that's created, the angle pair is made up of the two sides that are not congruent. I don't really know a better way to say that, but it's exactly one. And the book actually just goes with exactly one. And that one pair is that pair of angles, is the pair of angles that's formed by exactly one. It's definitely going to bisect these. It will bisect these pairs. It won't necessarily bisect this pair, but it will. Let's get a third one. Sorry. There's one pair. This was the one I was thinking of before I wrote bisect. One pair of congruent angles. That's what I was looking for. It will bisect, so we'll make three. It will definitely bisect this pair of angles that are not necessarily congruent. It'll bisect, a diagonal will bisect the pair of angles formed by each of the pairs of congruent sides. And we actually get a congruent angle. In fact, we get the pair of opposite angles that are formed by the sides that are not congruent will be, those angles will be the same. So let's get actually a bigger drawing of this thing. This might help out. Okay, so we have two things. First of all, diagonal will bisect one pair of angles. One diagonal bisects this pair. We also, oh boy, what other pair of angles needs to be, what pair of angles in the kite should be congruent based on this drawing? Yeah, based on these congruent triangles. The pairs of angles that are between the two pairs that are different lengths also need to be congruent. So in our original kite, these two angles, or the angles between the two different sides, are going to be the same length, but not these two angles. Almost will never be the same measure, but they will be bisected by the diagonals. Yeah, that may sound convoluted, and I did not intend to do that. But these two angles are congruent. These two are not congruent, but they're definitely bisected. They're cut in half, which is good. So I can ask you to find some missing parts. Like, for example, if I give you this, which one of these angles should we know, like, off the bat?
K.
We should definitely know K just from the information given, because K is the angle that's between the two sides that are different, that is included there. So K needs to be the same length as M. So angle K is 88 degrees. And if you know those three, then you can find J for sure. How would we find J? Yeah, we're kind of this is a four-sided figure, right? What are the sum of the angles of a four-sided figure end up to? 360. So you could say 360 is equal to what, 88 plus 88 plus 120 plus whatever angle, the measure angle J is. And you can find angle J. Is it 240 minus 172? 176, 64. So angle J has got to be 64 degrees. So 2x has got to be the same as 111. 2x is 111 divided by 2. X is what here? 50. 5.5. So this is going to be 111. This is 111. So we have 222 plus 80 is 222 plus 180 is 302. So then what's this angle? Again, same idea. Add the three angles together, subtract that from 360, and we'll get our missing angle. If I give you these crazy diagrams, how are you going to find the missing sides of a kite? What do you know about the diagonals of a kite? What's true about them? What was one of the properties you just wrote down? They're perpendicular. Okay, so what's that mean that we can add to this drawing? What can we add into this drawing? Right angles. And how about a right angle there? Oh boy. If that's a right angle, then what's this thing? Oh boy, so if I want to find this missing side, how about you use Pythagorean theorem to find missing side? So for this side, we have what? 5 squared plus 12 squared is c squared. 25 plus 144, 169, plus or minus 13. We won't do negative distance, so c is 13. You could do it again, or you know that we have two pairs of congruent sides. So if this is 13, then this is also 13. So then we'll have to do Pythagorean theorem one more time to find one of these missing sides. This is actually a nice case in that, well, what you can, if you want to use Pythagorean theorem, you can. What kind of triangle is this? So isosceles, what's another name for this isosceles right triangle? Oh, if we classify it by its angles, we look at special right triangles. This is any isosceles right triangle is at 45, 45, 90. So what would be a really quick way to get this length? Yeah, we could use your special right triangle properties without even using Pythagorean theorem. You could get this is forced to be leg times root 2. So this side must be 5 roots of 2, which is this must be 5 roots of 2. Okay. You can do the same with B if you want, but we're going to stop.